Now that we've looked at the temperature and pressure dependencies of delta G independently, we can now put those two pieces of information together in order to develop a model or an equation for determining where this phase boundary or coexistence line is between our alpha and beta phases. Okay? All right, and so what we know is at this boundary line, the alpha and the beta phases can coexist, right? You could have both, liquid and vapor at that line, or both solid and liquid at that line. And the criterion for that is that the difference in the molar Gibbs energy between the two phases is equal to 0. Okay? All right, and so we see that this line is a function of pressure and temperature. All right? And this line exists wherever delta G is equal to 0. And so, mathematically, what that's describing is the change in pressure as a function of temperature at delta G is equal to 0, or where delta G is a constant and its value is 0. Okay? And so, graphically, this is what we see. And mathematically, we could describe it as a partial derivative of pressure with respect to temperature at constant delta G. All right? And so, now that we have this partial derivative, how can we turn it into something that gives us actual numbers? Okay? And so, we have this here. And what we could do here to turn it into something that could allow us to calculate values is we could apply the triple product rule. Okay? All right, and so from the triple product rule, we could turn this dp dt at constant delta G into d delta G dt at constant P and d delta G dP at constant T. Okay? All right. From the fundamental Gibbs energy equation, we know that dg dt at constant P is equal to negative S. Since we have this negative sign out here, turns it into a positive S. And we know also from the fundamental Gibbs equation that d delta G dP at constant T gives us molar volume. Okay? And so, if we just write the deltas out, what we get is that that slope, that line, that boundary line between the two phases, is just the ratio of the differences between the entropies and the molar volumes of the two phases. This ratio, which is pretty simple actually, is known as the Clapeyron equation. Right? And its utility is that the Clapeyron equation determines the phase boundaries in a pressure versus temperature phase diagram. Okay? All right, and so let's go revisit the carbon dioxide phase diagram here. Okay? And so we see all these coexistence lines that we have here, they all have positive slopes, right? And that's because, once again, dP dt constant g is equal to S beta S alpha over V beta V alpha. Okay? Alright, and as I mentioned before, by convention, the beta phase is the phase that has higher entropy. Okay? And so in our numerator, when we have S beta minus S alpha, if the beta phase has higher entropy, this numerator is going to be greater than 0. And generally, for most chemicals, the phase that has higher entropy also has a higher molar volume. So generally positive. Okay? And so for that reason, that's why you see all of these boundaries have a positive slope in this phase diagram. But that's not true of every chemical. In fact, in particular, for water, we don't see that for the solid to liquid phase boundary. Okay? And that's because for water, the molar volume of liquid water is less than the molar volume of solid water or ice. Or another way of saying that is that the density of solid water is less than the density of liquid water, right? That's why ice cubes float, okay? All right, and so since V liquid, or the liquid phase, which has the higher entropy, because its molar volume is less than the molar volume of the solid, the denominator in dp dt constant g, so SL minus S solid, or ice, I guess, because this denominator is negative, that ends up giving this phase boundary line a negative slope. Okay? And so that's just one, once again, the Clapeyron equation allows us to determine the direction of these phase boundary lines. Okay? A couple of other things to point out before we go even deeper into understanding these phase boundary lines. When we look at vaporization, so liquid to vapor, or sublimation, so solid to vapor, the molar volume of the vapor phase is just much larger than the molar volume of the liquid or the solid phases. And often, when you look at different chemicals, the molar volume of the vapor phase is about 1,000 times larger, or 3 orders of magnitude larger, than the molar volume of the liquid phase. Okay? All right, if we take a look at melting transitions, going from the solid to the liquid, okay, the delta V between the liquid and the solid phase is pretty small. Or in other words, for most chemicals, the densities of the liquid and the solid phases are pretty close to one another. In fact, the delta V between liquid and solid phases is usually only about 10% of the value of the density of the liquid phase. And so for this reason, when we look at the solid, and once again, this is in the denominator, and so if you have a smaller number in the denominator, that means you have a larger slope, right? And so in general, we see that the solid liquid line is just much steeper than the liquid to vapor or the solid to vapor phase boundary lines. So if we look for water, or look at water, we see this line's really steep between solid and liquid, while between solid and vapor and liquid and vapor, the line is kind of flat. And you also have to remember in these phase diagrams, a lot of times the y-axis and maybe even the x-axis are on crazy like log scales or something like that. And so we see this for water, and we even see it for carbon dioxide as well, where the solid to liquid phase line is very steep, while the ones between solid and vapor or liquid and vapor are generally more flat.